So next is characteristics of polynomial functions in factored form. So first we're going to start with a warm-up. Given the following polynomial function, notice it's in standard form since it's written with decreasing powers of x. I want you to state the degree of the following polynomial function, the leading coefficient, and the end behaviors. So starting with the degree, we see that this polynomial function is of degree 5, the highest exponent in the expression. The leading coefficient is the number in front of the variable with the highest exponent, so that would be 4 in this example. And finally, the end behaviors. So since this function is odd, that means it has opposite end behaviors, and since the leading coefficient is positive, that means it's going to behave in a manner where it goes from negative infinity to infinity. So since the degree of f of x is odd and the leading coefficient is positive, as x goes to negative infinity, y goes to negative infinity, and as x goes to infinity, y goes to infinity. So which differences are constant? Again, looking at the degree of this polynomial, it's of degree 5, so the fifth differences will be constant. What are the maximum and minimum number of zeros? Again, since the degree is 5, then our maximum number of zeros is 5, and since the function is odd, our minimum number of zeros is 1. What are the minimum and maximum number of turning points? So again, since the function is odd, we can have 0 turning points. And since it's of degree 5, we have to have 5 minus 1, so we can have a maximum of 4 turning points. So next, let's go on to our new topic, the factored form of a polynomial function. So as we look through each of these diagrams, we're going to describe the shape of the graph near each zero and compare the shape to what's called the order of each factor in the equation of the function. The exponent to which each factor in an algebraic expression is raised is called the order. So for our two examples below, we see that the x is of order 1 and the x minus 3 is of order 1. However, in this example here, we see we have an order of 2 because the exponent for x plus 2 is 2. Second part we're going to do is also solve for the zeros and compare the solutions with the zeros of the graph in the corresponding function. So let's go through the first example. So first of all, let's identify the zeros. So we have a 0 here at 0 and a 0 at 3. So we have a 0 at 0 and a 0 at 3. You notice the order is 1 for each of those factors. And if we zoomed in on this graph, we see that at that 0, it looks like a line passing through each of those zeros. Now let's solve for the zeros. So we're going to let f of x equals 0 for the algebraic expression, and we get 0 equals negative x, x minus 3, and recall if we want to solve for the zeros, we set each factor equal to 0, and notice we get x1 equals 0 and x2 equals 3. So we can solve these algebraically or we can look at the graph. Let's look at our second example. Here's the 0 here. So from our graph we see that our 0 is equal to 2. If we were to zoom in on that graph, at that 0 it looks like there's a parabola touching that 0. And that has some relationship to this order that we just discussed. So let's find the zeros. So we're going to let f of x equal 0. And we get 0 equals negative 1/2 x plus 2 squared. And if we want to solve for the zeros, we set our factor equal to 0. So we get x plus 2 equals 0. It doesn't matter that it's squared. And we end up with x equals negative 2, our only 0 for this graph. Let's go to the next one. Notice there are 3 different factors, and we have 1, 2, 3 different zeros. x1 equals minus 3, x2 equals negative 1, and x3 equals positive 2. If we were going to zoom in on these zeros, notice they look like straight lines going through the zeros since they are of order 1. Again, we can go and solve for each of these zeros, so we can let f of x equal 0, and that gives us 0 equals 1/2 x plus 3, x plus 1, and x minus 2. And if we set each factor equal to 0, I'm going to get x1 is equal to negative 3, x2 is equal to negative 1, and x3 is equal to positive 2. Next, we're going to look at a cubic that has an order of 3. And notice if we look at the 0, so x equals negative 2, that if we were to zoom in on that 0, that would look like a cubic function passing through the 0. Notice a cubic shape as we go through the 0. Linear shapes as we go through those zeros. Again, we can solve it and we will get x equals negative 2. Next one, notice I have an order 2 and an order 1 factor. So here's our order 2, and this one's an order of 1. Notice for our order 2, which is going to be a 0 of 1, it looks like a parabola around that 0. Whereas the x plus 2, which gives us a 0 of minus 2, it looks like a line passing through that 0. So we have zeros at negative 2, and we have a 0 at 1. Again, this one is of order 1, and if you look closely at the graph, it looks like it's passing through as a line. And this one is of order 2, and again, this looks like a parabola when it touches the 0. Next one is a quartic function. We have an order 2 and 2 order 1 factors. Let's start with the order of 2. That's going to happen at negative 2, and notice at negative 2 we have a parabola touching the x-axis. And for 1 and 3, they look like lines going through the x-axis. So again, our zeros here are x1 equals negative 2. That's the one of order 2, and it looks like a parabola. We have x2, which is of order 1, and we have x3, which again is of order of 1. And that helps you determine the shape at the zeros. Finally, look at this quartic function. It has an order 1 factor at 0, and notice it does look like a line going through there. And we have an order of 3, which looks like a cubic function passing through that 0. So we have our first 0, we said was at 0, and that is of order 1, which looks like a line passing through the 0. And our second 0 is negative 3, which is of order 3, which looks like a cubic function passing through that 0. Remember, a cubic function looks something like this. Or the negative of it looks like this. So one final time, if we wanted to solve for these zeros, let's do the left one. So let f of x equal 0. So if you didn't have the graph, you would say 0 equals 1/4 x plus 2 squared, x minus 1, x minus 3. You said each of the factors equal to 0. So this one's going to give me my negative 2. This one's going to give me my positive 1. And the final one is a 0 of 3. So how does a linear square a cube factor in the equation of a polynomial function affect the shape of its graph near the corresponding zeros? So we saw that if any of the factors of a polynomial are linear or of order 1, then the graph has a linear shape near the zeros. So looking at this -2 and then zooming in, you see you have a linear shape. If any of the factors are squared, then the graph has a parabolic shape near these intercepts. So looking at this here, that would be of order 2. And notice if we zoom in, it would look like a parabola near that 0. And finally, if any of the factors are cubed or of order 3, then the graph has a cubic shape near that 0. So let's look at how we can use that information. So example 1, determine the equation of the function shown below. Well, first of all, we need our zeros. So starting with this one, we see we have an order of 1. Since the curve looks linear as it passes through that 0, the next one, of course, is of order 2 because it looks like a parabola at that 0. And the final one here is of order 3 because it looks like a cubic function as it passes through that 0. So to find an equation in factored form for any polynomial, we start off with the following function. Y equals a, x minus x1, x minus x2, x minus x3, and so on. In this case, we have 3 sets of zeros. So at -2, at 0, and at +3. We also have to state the order in each of these. So the order for the first one is 1, the second one happens to be 2, and the third one is 3. So those are the exponents we need to put into our factored form. So next step is to sub in our zeros. So we have y equals a, x minus 2, so that's x plus 2. The next one's x minus 0, and the final one is x minus 3. Don't forget our exponents. Our exponents are 1, 2, and 3. So subbing in our point, we get -24 equals a, 1 plus 2 to the exponent of 1, so that's 3. Then we have 1 minus 0, so 1 squared, and -2 cubed. So this gives me -24 is equal to a times 3 times -8, so -24, and we end up with an a value of 1. So therefore, f of x equals, our a value is 1, and then we have our x minus 0 squared, so I'm just going to write that at the start as x squared. And then we have our x plus 2 and our x minus 3 all cubed. Example 2. Let's try this again. Determine the equation of the cubic function that has zeros 5/7 and 2. And the 2 is of order 2. We'll start off with y equals a. This time we have 5/7. And that is actually 7x minus 5 to the order of 1. And then x minus 2 to the order of 2. So you might say, how did I get that? Well, let's work backwards. If I have 7x minus 5, and I know that's one of my zeros, if I move the 5 over, I get 7x is equal to 5, which gives me that x is 5/7. And similarly, if I have x minus 2 equals 0, and I move that over, I get x equals 2. So there is my 0 at 2, and there is my 0 at 5/7. We also have the point 0, 12, so that's where we're going to sub in for x and y, and determine the equation for this function. So -12 equals a, -5 to the exponent of 1, and -2 to the exponent of 2. So -12 equals a, so that's going to be 4 times -5, so that's going to be -20. And therefore a is equal to 3/5. So our function we have is 3/5 7x minus 5 times x minus 2 squared. So it says sketch this function. So again, it's just a sketch. So we have a 0 at 2. We have a 0 at 5/7. So let's say that's here. And we know our graph passes through 0 and -12. Let's say that's there. This is a cubic function. So it's going to go up. Remember, this is of order 2, so it's got a touch as a parabola. The first one has to go through as a line. And there is a graph of our cubic function. The good part is we see that this a value is positive, which means our graph should behave in this direction, going from -infinity to infinity for the end behaviors. Because of the positive leading coefficient this function would have if you expanded the expression. All right, final one. Sketch the graph of the following function. And the key things are to look first of all for your zeros. So if f of x equals 0, then we have that 0 is equal to -x, x minus 3 squared, x plus 2 squared. Our zeros, you see, are at 0, are at 3, and are at -2. So let's graph those. So -2, 0, and 3. Again, this is just a sketch. So if we were to expand this expression, notice we have an x, we would have an x squared here, an x squared here, and an x. So this function would be of degree 5. We also see that we have a negative here, and it's the only negative in front of an x. So this would be a function that has a negative leading coefficient. And with this information, since we have odd degree and a negative leading coefficient, our function should look something like this. It should go from positive infinity to negative infinity in terms of the end behaviors. So let's go that way. So that means it's going to come from positive infinity at -2. It's of order 2, so it's going to make a parabola. Then it's going to go through 0. Since 0 is order 1, it's going to be a line going through 0. And then for the 0 at 3, it's of order 2 again, so it's going to be a parabola touching that 0. And then we just add our arrows. And there is a rough sketch of this polynomial function. Complete the following 4 questions from your book. And if you have any questions, contact me right away.